to abbreviate the aluminum bromide like this, since the purple stuff does not really, it just stays the same. Is that okay? Right? Let me just, yeah. So I'm going to take this part, which is aluminum PR4 minus right here, copy and paste it over here. Just like that. So we're going to have okay, so here's the PR. Okay, and then of course, so we take this again. You might see variations of this. Somebody might say, well, this leaves, but then after it leaves, it picks it up. So I'm trying to keep it as simple as possible. I'm taking this bond. I hope you agree. Let's have a parenthesis here. If this leaves, then you got back aluminum bromide as it's here, and you have a BR minus floating around and picking it up. So if this breaks, then you have a low paratype. But let's simplify it. Just have this two green dots. Come and pick this one up, and then this will collapse, right? And let's let me just change the color slightly, and so that way you don't get confused. Let me use like this, because I have black arrows meaning resonance arrows. I didn't do the last one here. Well, the last one here is going backwards, right? Yes. I mean, you know how it goes from the arrows, right? I mean, this would be label B. The other one would be label C, and that would be what would that be? B, right? Okay. So anyway, just change the color to orange so we don't confuse the arrows with the arrows of elimination here. So having done this, the final result will be getting this, and then this, and then this. The CH3 is still there. The carbonyl is still there. And then bond closed. Right? So you can see this closing there. Okay? And so we got the final product. Now, can I use B to get the same thing? No. The middle structure is there to show us that this is called what? The sigma complex is all the three resonance structures, which is stable because of the resonance. Now, one important thing here is this is tertiary, right? And then this is secondary, and then this is secondary. And this is to prove that if you do the substitution over here, the plus charge travels in ways where it puts a tertiary carbocation, which is very stable, right? Versus secondary. If you put it on meta, you get secondary. We'll try this in the lecture, right? And of course, if you do ortho, it will still be secondary, tertiary, secondary. So the reason we do the sigma complex is to get at least tertiary. Now, can C also give me an answer here? C will also give me, so you don't have to do both. You shouldn't do the both, because I'm not asking the exams both. But I'm just saying one student can do one student can do the other, both will be correct. But don't do it from the middle one, because it's not going to work. Right? So, okay, so same idea, right? Let's find a hydrogen here. It's the same kind of hydrogen. So you pick it up from here, and then this collapses, and then how would you write your final structure? Slightly, it's the same thing, just the double bonds. If you want to be consistent, it would be like this now, right? Okay, and then of course this is the new bond. I make it in orange. That's how it was made. Okay. All right. Any questions? Actually, there's a few more things. There's additional substitution. One more thing. So, I guess we answered the question: what will happen? Consider whether an additional substitution will take place. What I really mean by additional substitution is the following. Right here, this is disubstitute now. But here, it's the same thing, right? So, if you want to put more stuff here, can you put one more of this electrophile over here? And where would that go? Because that's we have access. And this is practicing with the problem number 5 in 5 and 6, you're going to deal with this. So this wants to put things where? Ortho and 5, I guess. This blue one, after it's placing itself here, wants to put in meta, right? So there will be an agreement. This methyl group wants to put things on ortho. This position is meta to the blue one, so if there is another group, it will be over here. Yes? That's what I mean by addition, or the word is addition. I guess the word I was doing also, I don't have it writing, but is there an alternative substitution? We already answered this. What is the alternative substitution? Instead of attacking here, we'll be attacking from here and making also the what?
Ortho.
The ortho product, right? So make notes of this. It's also important. And finally, consider what would be different if bromine was used in the presence of the same catalyst. So, if this was not here and we use Br, how would you put bromine here? First of all, you will keep this, but instead of Br, will be Br2, right? So Br2 plus this, we'll go through this, instead of this, will be Br plus. So the same thing will happen again, instead will be Br, right? So again, that's things, write them down and practice the same thing, 80-90% of the same. Yes? Yeah, I mean, I didn't say we'll get a big hill, but I mean, if you want to see, you'll get a small.
I mean, the
Because the
Yes, so benzene, but here has a methyl
because
group.
now you have 262.
The guys here said, you know, if you have a benzene, methyl benzene is less reactive. But here there is a methyl group there too. So I'm not saying what is the percentage of the product, just say what other products you may get, 1%. But this is the major product.
But then that one.
Did this go out when I was talking? Was I talking? I mean, I used this when I was talking, no? I'm just eating, you don't pay attention. Did I use the microphone?
Because you have two different.
Just like, you know,
Yeah,
just
that'll be
chew
the best.
harder so I can get a hand. Okay. All right.
I actually think I know it. Yes, that's a no. I know the mechanism. Yes. When you got tissues. Talks about
Okay, so this next problem is about starting with nitrobenzene. Okay, so let's have nitrobenzene. Okay, and now we will place the nitrobenzene over here. Let's actually write it a bit more carefully, the nitrobenzene. Write it with its full Lewis structure. Okay, that's a nitro group. I mean, I'm not going to go show it all the time like this, but no, just get familiar. And it says to use fuming sulfuric acid. So we're going to use SO3, we write like this. And again, let's be detailed in the first part, and then we might forget to write all of them again. Right? And then you're going to use sulfuric acid. Okay, so we're going to use sulfuric acid here. Fuming, right? Very strong. So really, fuming sulfuric acid means you have sulfuric acid, the one you're familiar with, very concentrated, and if you steal, so to speak, SO3, what you're left behind. You lose this, you lose this, you lose 3 of them, you're left with 1 oxygen H2. That's H2O, right? So SO3 is coming out as fumes, leaving behind water, right? So it goes into equilibrium. Anyway, this is electrophile, so to speak, but let's check the electrophile. So, I mean, just to confirm it, right? So in order to prove that this is electrophile, we have this. And so you can do some resonance structures. So you can do resonance structure here, and of course it gives me this. Okay, and then of course you can do this, Okay, and now it went from 12 o'clock to 4 o'clock. Okay, and I guess we'll do one more. This one here, and finally, I have to be careful what I write here because it might jump slides and then erase it. So bear with me. Survive without it, slide getting, without getting there. Okay, so when we do these things, hope you realize we have the following charges: plus and minus, plus and minus, and plus and minus. We do all this work to prove again that you have what? You have an electrophile, and there are 4 ways of looking at it, right? Because when you look at it in the beginning, it doesn't look like it has an S plus charge. They're all 0, 0, 0, and this is 0, but it's plus 1 and minus 1. So you see there's somebody plus charge residing over here. Okay, so according to this, one more time, we say this is an electrophilic aromatic substitution. And because it's electrophilic aromatic substitution, we can address 3 things. Well, the first thing, I should have addressed this thing before I even talked about this. This first bullet, you can answer it without doing any of this. Is this electron withdrawing or electron donating? That's electron withdrawing group, right? Okay. And after you ask the question, is this meta-directing or what is it? Well, it depends, the answer is. It depends what kind of reaction you have. And so you do all of this, you have an electrophile, because electrophilic aromatic substitution, then if you have an electron withdrawing group, electrophilic aromatic substitution, what is that? It's a meta-directing, right? And of course, it's also deactivating. Actually, the order should be like this: 1, 2, 3. Doesn't really matter 2 and 3, but I mean, just technically, first we say it's deactivating. Let's do the mechanism of this. Okay, so we take again these benzene ring. Okay, and now let's abbreviate this. And we have the SO3. Now, the SO3, you can write it this way, or you can write it this way, because it already has the arrows, right? So, I mean, I can use any of these structures. So I think it's easier to take the one that it already has a plus charge, right? I mean, so here it is. So that way we kind of keep it the same, but anybody can use any of the 4 structures. Not all of them, but any of them, and it will still be correct. Okay? Because you agree this is a minus and that's a plus. This plus that I'm writing right now, that's important, right? And then of course, you have the attack over here, so similar idea as before, okay? So now, the choice we have is to put it, because of all the things we said in 1, 2, 3 in red up there, we need to put it in the meta position, yes? So we have the NO2 here, and then we're gonna have this over here, and let me see, sulfur. I think I need enough. I think I have enough space to do the resonance structures. I'll do that space out. I think we're going to use all of this for resonance right here. Okay, and here's the oxygens. And there's one more oxygen here. And this stays with a negative charge. Now, let me just verbally say this. This can get protonated, and finish with this, or we can do the shape up in the, in the very end. Okay. Now the double bonds are still there, those two, right? Okay. And then of course you're going to have a plus charge, right? So you're going to have the plus charge put over here, and mind you, let me just highlight this hydrogen and have it over here, right? Of course, there's a hydrogen here too, and there's hydrogens around everywhere. But again, I put in color the one that's the important one to pull out. Okay, so let's do the resonance here. All right, and now for simplicity, I will still keep the NO2 collapsed. And I will just say here SO3, just look at the resonance structure. And again, let's see, so this goes over here. Again, we're going to call this A prime, B prime, so this is the little A. And of course, if I do that, the plus charge transfers over here, but then this is over here. Okay, and what else? I mean, because the plus charge is special, I'm just going to highlight it here. Okay, and then one more. We do this, and as a result, the plus charge will move over here. You still have the NO2. You still have the SO3. Okay, double bonds are over here, Okay, and then probably C prime, and I guess you can call this C prime, and if you want to go back to the D prime, you can do this. Alright, so this is the resonance. Now, I left a little bit of space because how many more resonance structures can we make? I'm just going to put it here, and you say you can do one with the NO2 group, right? Yes. So more resonance if you include so one resonance for the NO2 plus how many resonance for the SO3? We have it up there, right? You see that? Okay. So plus two. Well, I mean, one more for the NO2 and two more for the SO3, because in other words, what I'm trying to say is that this is one of them, right? So be two more because this cannot be there because each one of them will. So this is like a little detail in your practice of this, but this is the crucial part. Okay, so let's concentrate on the important part. And of course, in exam I might tell you I need 3 resonance structures. That's important. I need like 4 or 5. But this is the big deal. So don't get stuck here. But don't forget also there's resonance here. Okay. Now we need to finish it up. And again, we need to abstract this hydrogen. Who is going to abstract it? Because here, we have, so let's think about what happens also. We need to have a conjugate base, right? And the conjugate base we have, it can be one of these, right? There is a minus here, but also think about the following. One of these hydrogens is over here, so we can have a use of sulfuric acid like this. So let's kind of do this. Here would be a good place to write it. This is sulfuric acid, and this goes in equilibrium, right? It has all these long pairs, right? So this oxygen here, let me use a purple one actually to kind of highlight it, right? So this is the sulfuric acid, so it stands out, right? So this one here can come and pick this up, and so in the end you will have, this will release sulfuric acid, which is this, okay? The conjugate base of the sulfuric acid. Basically, you need this. Somebody can argue, well, these are all in equilibrium that you get all of this to do this. Anyhow, you need some of these pieces that are floating around to pick it up. So this comes and picks up the hydrogen that was saying about earlier. Let's do it with a purple arrow, so to speak. Picks this up, and then of course this collapses. And so the final product will be like this. It will have the NO2, it will have the SO3, but the SO3 now, it will be, let me do this in purple, right? I'll just do purple on the sulfuric acid, so you can see this purple H I'm writing right now came from this purple sulfuric acid things. Okay, just so you can orient yourselves. Okay, and then of course this double bond closes, and I can make it with orange to know that where it came from. Okay, and of course the B cannot do this, right? But the C can also do it. You know, same idea. Of course, this would give me the opposite. Would give me this kind of situation, right? And SO A H. Okay. So let me. Any questions as I'm addressing the other issues? Any questions? Draw the mechanism of the products to the reaction with nitrogen with sulfuric acid. What is the name of this reaction? So what is the name of this reaction? Yeah, this one we call it also sulfur. So the name of this reaction is sulfonation reaction. The mechanism is EAS, right? Because sometimes I ask you the exams, you know the answer, but you don't know how to fill in the blanks. What is the name of the reaction? Is sulfonation. What kind of mechanism it is AEAS, electrophilic analysis. Consider whether additional substitution can take place and in which position, right? So this can continue with SO3, right? And create this, right? NO2, SO3H, and what will be the other SO3H? It will be over here, right? Yes. However, this is going to be very difficult, right? It's going to be very small amounts, right? Due to what? To having two deactivating groups now, yes? But if you form something, let's say less than 1%, you know, because you know you can form, right? Use heating, leave it for a week, you know, whatever, right? Then you might get something but being very, very tiny amounts because the whole thing is deactivating. You may remember, deactivating means you get a very low yield, right? That's number 2 statement. It's wrong. It's deactivate. And then here you have two deactivators, deactivated, and meta position is the less problematic, so to speak. Yes, you will get it from the very, very tiny amounts. And that's it. Now, needless to say, when we do this, here there is no other alternative substitution because there is only one meta position. Whether you put it over here or here, it's the same thing. Right? So this is addressing the issue of additional substitution. Okay. Any other issues? This is too nice. All right. Do you guys finish everything? Make sure you have your carrots. Is that carrots?
Yeah.
Yeah, carrots next to cupcakes. Just keep the carrot there. Yeah. All right. Now, next is on the mechanism and the products of the reaction of one product. By the way, problem number 3 didn't have a typo. I think it's okay, right? I think on Tuesday, problem number 3, the number 4 was missing. So just make a note. Somehow it corrected, but somehow in the printouts. So we have the reaction. Okay, all right. So okay, so So now we're going to use this molecule. Okay, here's a benzene ring, but it says to use one bromo. So I'm going to use bromo here, and I'm making the bond green because we know that bromine likes to take the electrons with itself. And what else? We have a nitro group. Let's also mark this here. The nitro group. Again, writing it in full Lewis structure, but then we can always abbreviate it. And then we have sodium amide. Okay, so let's write this NH2. This is a lone pair here, and then this is a minus. And then the sodium is a spectator ion. That's sodium amide. By the way, what else do we have here? We have heat. And sodium amide is solid, right? So in order to dissolve it, you need to dissolve it in ammonia, NH3 liquid, right? So you have an H2 solid, you dump it in liquid ammonia. So I'm highlighting in color the important parts, right? Okay. And of course we have heat. Now, this thing here, before we answer questions about the green and the red and the benzene, let's answer questions about this. This is what? A very strong
Base.
what?
Base.
Nucleophile and base. And base, yes. But it is a nucleophile. So the mechanism would be what? So the mechanism would be what? NAS would be nucleophilic aromatic substitution, right? Okay. So if it's a nucleophilic aromatic substitution, let's address the issues again. So this one here again, this can be answered without doing any of the stuff I did. Just so this group here is what? It's electron withdrawn, right? It will be withdrawing without any other questions asked or anything else. But because it's a nucleophilic aromatic substitution, so let's actually say this in NAS, right? This electron withdrawing group will be activating or deactivating. Yeah, it will be activating which positions? The ortho and the para positions, right? Okay. And so it's activating the ortho and para positions, right? And so, I mean, you can say directing, but you see, there is no issue here because it's already a leading group there. So you can use the word directing or activating the ortho para positions. Okay, let's understand this a little bit better. So if you look at this carbon here, what is the charge over there? Delta plus, right? And what is the charge of the bromine? Delta minus. I'm going to make this up. I will say the delta plus is 0.7 and the delta minus is minus 0.7. I'm making this up. It's not plus 1 and minus 1, right? Obviously, otherwise it would be ionic. So what we're saying is that if you have a bromine on the para position, and you do, or if the NO2 was over here in the ortho position, either or if you have another NO2 here, would be good too, because you have NO2 here and NO2 here, then what they will do is they will make this delta plus even bigger. Let's say this 0.7 becomes plus 0.9, okay, plus 0.95, whatever it is, right? Okay. So it makes it more electrophilic. So what we're saying, it makes the carbon delta plus on the carbon bromine bond or electrophilic, yes? Right. Okay, so it makes this more electrophilic. And of course, what's going to happen now, we have the nucleophile in purple, we have an electrophile, an electrophilic substrate, which is black and green together, black, red, green. But the electrophilic side is not the carbon, right? So what we're going to do is we're going to take this and make it behave as a nucleophile, and it will come and attack this, yes?
Yes.
And then, should you do this? The answer is no. Don't kick out the bromine yet. That's the key word. Don't kick it out. Again, this is very similar to what we did the acid bromides and alcohols and so forth. So leave it there because that's something that you might do. So let's write it nice and clean. So all this was the work just to understand it. So let's write it nicely here. So we have the NO2. I have this over here. And so we have the bromine. Actually, not to waste time, we can just, because we did the first step, right? So, by the way, so instead of doing this, what we should do instead is open this up here, right? Yes? Right?
Home curves.
And so we need to gently open this up here. Okay? And have the nucleophile over here. Okay, so we have a lone pair, and of course this can do resonance. So the lone pair will travel around. Okay, and the NO2 is still here. So let me actually at this point open up the NO2 because we can ask questions whether we can do another resonance structure there. Okay. And let's do one more. So here is this. Okay, I'm not putting the rest of the lone pairs, but of course you know how to put this there. And let's see, just trying to think about whether the resonance structure of the nitrogen can do it here or not. Alright, that's fine. Yeah, okay. No, I know. Just So I'm just going to collapse the NO2. And so this is the three resonance structures. Here we can close this. I will ask about the resonance. Here actually we can throw one more resonance structure. Let's just verbally mention that over here. But we can finish it up now. So let's go back to this. This is arrow number 1. That's crucial, right? That's arrow number 1, purple. And then this is arrow number 2, the black one. So one more time. Purple arrow is number 1. Purple, green, black arrow is number 2. So let's see how we can finally get this, reaction to take place. So I'm going to use a different color again. So look at, again, I'm going to call this A prime, B prime, C prime. Okay. So if you look at the A prime, and you take this lone pair now, and you collapse it, look at my orange arrow. Right, so the black arrows are resonance arrows, right? So I use different colors, don't get confused. But if you take the same lone pair and you collapse it, right, then you can pick out the bromine with this green one. So the 4 crucial arrows, I'm repeating myself, but that's very important, is arrow number 1, black arrow number 2, orange arrow number 3, and actually we can even mark them, right? Because this is important. Number 1, number 2, number 3, like stepwise, let's take number 4. Okay, so this is we said the mechanism in AES, but more specifically, the mechanism is what? Look at the purple arrow, number 1. Is it adding or is it substituting? Addition. And look at step, the orange and the green, 3 and 4. Right? You have addition and elimination. So I'm going to use the colors. And I hope the colors help you out, right? I mean, the purple is addition, the purple arrow is addition. The green arrow, number 4, is elimination, it eliminates it. But black 2 and orange 3 is like back and forth, right? I mean, that's opening up, closing down. Yes, makes sense?
Yes.
So we call it addition, elimination. Okay? Let me just erase myself. Did I forget anything? Let me say, if there is, let's say you want to do an order, now, resonance structures, you can do them in several ways, but I mean, you can also do this kind of thing. I will allow it just for convenience, instead of erasing everything and squeezing it, because somebody could argue, you know, like I did a resonance structure, well, A, B, C, and D this way, but let's do one here, right? Because that's convenient. So let's do, somebody can do this with a different color, right? Okay, and then you can do this, right? So, so in other words, you can do 1, 2, so you can do, I would say, and if you do a resonance structure, actually, to tell you the truth, this is an important resonance structure to write, so let's not skip this one. Let's draw this one. This is not insignificant. So if you look at the red arrows, which I would call it D, let's see here. It's this one here. Then it's going to be like this, and then it's going to be like this. Okay, and so we have. What else now? We have a plus. Of course, we have another plus here. Okay. And of course, now that's where I will just say that you know. Then, of course, this can collapse this way. This can collapse this way, and you know, open this one up, and basically you get the other resonance structure of this, right? So you need to say plus 1 more resonance structure. On NO2, right? And you know, they're all correct. I mean, would you do it? I mean, this one has to be done here. It cannot be done anywhere else, right? I mean, and of course, somebody can travel from this to this one. So if you want to go A, B, C, D, you can do this like go this way, this way, this way, and then you collapse this, and you open this up, and then you get this. So it's kind of the same idea, as long as you have the 4 of them there. Okay? And, you know, I mean, there's one more really, if you want to do all of it, it's really fun. So, what else? Okay. Nothing else I'm forgetting, right? I have this. We didn't do the product. We didn't write the product. So we didn't write the product. So, as 3 and 4 takes place, so here is the product, right? So it's this, NO2, and NH2 over here, and so then you have this. I'm going to make it with orange so you can see it. Okay. This is from A. Can also B give you a product. I mean C, right? Same idea, right? So if we do this one here, and then this one here, you can also get a product from this one. So again, I'll do this many, many times to see that the edges of the resonance structure, so to speak, always gives you the product, and the middle one doesn't. Okay? So if there is something that's going to be consistent between each one's response, is going to be to write the beginning and the end of your resonance, and how you present it in the middle, it's okay as long as they're consistent. And so the product is really this. Okay.
I have a question.
Yes.
Why did the VR wait in the beginning?
The BR, no, because if you leave it at the beginning, it does not allow you to go through the resonance. So remember the sigma combo to the resonance order, that's what drives all the reactions.
Yeah.
It's the same question can be asked in Unit 11 about alcohols. When you have a carbonyl, I don't write here, but if you have a carbonyl chloride, right? I mean, you cannot kick out the chloride. First, it has to go through a tetrahedral. So this is an injection. The temperature gets lower, that allows the reaction to proceed. Right. Yes.
For structure B,
Uh-huh.
going to C on the resonance structure.
Yes.
So I thought the lone pair would go up, and then the bond would make the lone pair at the top to C.
So this lone pair that
Go to the left.
this arrow is wrong.
Yeah.
That's for that bottom there.
I did this on purpose again. See if you're gonna notice. Somebody caught that.
There we go.
Nice.
Half a point for her, right?
Isn't that arrow for that resonance going down?
And
It's the.
sorry.
For what?
Yeah. What's okay? So here's a little mistake that I did on purpose to see if you're gonna notice, right? So this comes over here, and then this should be over here. Okay? It's a typo, but you don't like it? Yes? You don't like it? Yes?
And do we also include the loss of VR minus for the transition to the product?
I mean, you know, in the end, like the beer minus. So you have in the end sodium bromide. Yeah.
That's a plus one.
Yeah. So let me double check again. That's fine. Anything else? Any other type of check? Do you agree? You don't like it, I give you half points. You don't like it, I give you half points. Is that fine?
I don't like
So what is the other? The double point is here.